So here we are on day 2 of Riemann sums, and today we're going to focus on the trapezoidal Riemann sum. So yesterday was strictly rectangle. The only other shape we're going to use is a trapezoid. So I first want to review the area formula for a trapezoid, and that is area equals 1/2, you can say height, base 1 plus base 2. Now I just want to reiterate, these bases are the parallel sides. Now, depending which way your trapezoid is facing, you could also say area equals 1/2 base, height 1 plus height 2. And in fact, this is the one, again, that we're probably going to focus on the most with these Riemann sums. Because, again, our parallel sides technically are going to be our heights here. So, just to remind you, to get the width of your rectangle, so very similar to yesterday, I'm going to take the difference in my integral bound, so the distance between those two, 4 minus -2, divide by the number of subintervals. So 6/3, so I'm going to have a width of 2. Now this does say we're going to have equal lengths, that's why I'm doing that, to make them all equal. So, I'm going to start with my blue trapezoid. So here's the base of the first one. It has a width of 2. Now this one's unique. When we said right, we went up on the right-hand side. When we said left, we went up on the left-hand side. Midpoint, we went in the middle. Trapezoid, and perhaps you could start or make a note to yourself, you actually use both the left and the right. You go up on both sides to create the trapezoid. So I'm going to go up on the left until I hit the curve. I'm going to go up on the right until I hit the curve, and then I'm going to make one straight line as best I can here to connect them to make a trapezoid. Okay, so you can see I have two parallel sides. There's my base, my height 1, my height 2, and there's my trapezoid. I'm going to go ahead and draw in my second trapezoid. Again, it has a base of 2, so count out base of 2. I'm going to go up on the left till I hit the curve, up on the right until I hit the curve, and connect them to make my trapezoid. And lastly, I'm going to go up on the left. Here's my base, up on the right, which happens to hit the curve right there. So this trapezoid, oddly enough, looks like a triangle. Okay, so now I just need to calculate the area. So this first blue one is 1/2, the base is 2, and I need height 1 plus height 2. So here's height 1, 1, 2, 3, 4, 5. Plus height 2 is 1. Take my green one. Again, I have 1/2, a base of 2. The height on the left is 1, plus the height on the right is 5. And then I'm going to add to that the last one, which happens to be a triangle. So 1/2, my base times my height. Now I could treat it like a trapezoid, and I might as well do that. Again, I have a base of 2. My height on the left is 5, plus the height of 0 on the right. Or I could treat it like we said, a triangle. So as I check my addition here, the halves and the 2 cancel, so that's 6 plus 6 plus 5. So that's 12 plus 5. I get an approximated area of 17. Again, not the actual area. A Riemann sum is an approximation. Okay, yesterday I didn't feel like we really summed up these pictures that we drew. So I want you to put this in your notebook. I want you to start with concave down, and we're going to do one that's increasing, and we'll do concave down, one that's decreasing. Okay, and let's draw a left-hand Riemann sum in both. So I'm going to go up on the left till I hit the curve, over and make a rectangle. We said the bigger you make the rectangle, the easier this is going to be. And I'm going to do the same here. I'm going to go up on the left, I'm going to go over and make a rectangle. Here's what's so important that I felt like we didn't really summarize yesterday. Does the concavity have anything to do with whether this is an over or under approximation? In both cases, they're concave down. This one is an under approximation, and this one is an over approximation. So I want to be clear, the concavity had nothing to do with this. My justification is going to be because this function is increasing versus decreasing. So let's get that in your notes someplace. Concavity has nothing to do with over or under approximations. Okay, it's all about whether the function is increasing or decreasing. And please don't memorize that. Simply draw a function that's increasing or decreasing and draw the picture in and you can answer the question. Let's check concave up. So we'll do concave up and increasing, concave up and decreasing. So concave up and increasing, concave up and decreasing. If I draw in, let's do a right hand this time. Up on the right till I hit the curve, over and down. Up on the right, over and down. Even though they're both concave up, it didn't matter. It's whether the function was increasing or decreasing, whether it was an over or under approximation. Now, there's one catch to that, and that's the lovely trapezoid. Okay? So let's draw two concave up, one that's increasing and one that's decreasing. Okay, so now when I go into my trapezoid, remember going up on the left, I'm going to go far, I'm going to make it really wide. Up on the left, up on the right till I hit the curve and make my trapezoid. Up on the left, up on the right, make my trapezoid. Now what didn't matter this time? The increasing, decreasing didn't matter. What it did depend on was the concavity. Since it was concave up, the trapezoid is an over approximation here, and that is because of the concavity. Okay, so we're going to have to keep these straight. It doesn't matter for the rectangles, whether it's left, right, or midpoint. We said the concavity has nothing to do with it. It's just whether the function is increasing or decreasing. But when it's a trapezoid, it switches gears on you, and it is all about concavity. All right, so same problem from yesterday, same table, in fact. We're just going to change the question a little. Use a trapezoidal Riemann sum with 4 subintervals to approximate the area from 0 to 8. Okay, so again, I'm going to break it up into 4 subintervals. So I'm going to go from 0 to 2. Now it doesn't say they're equal. Pick it up where I left off. 2 to 5, 5 to 6, 6 to 8. So those are my x's, those are my bases. My y's are my heights. So again, if you had to draw this out for yourself, which you don't have to, but if my base went from 0 to 2, and now a trapezoid, remember, goes up on the left and up on the right. So I'm going to go 0 on the left, up on 5, and then make my trapezoid. So this is an odd one that looks like a triangle again. Let me do the next one. I'm going from 2 to 5. I'm going up to a height of 5, up to a height of 9, and then making my trapezoid, etc. Okay, so the first thing I'm going to do is write all this out. So I'm going to I always start with my formula. 1/2 base height 1 plus height 2, and I just jot it down once so I have it to stare at it. So my first trapezoid is going to be 1/2. The base is 2, and my height 1 is the height on the left, which is 0, plus the height on the right, which is 5. Okay, and then I'm going to add to that the next trapezoid. Okay, so I'm going to start with my formula again. 1/2. The base goes from 2 to 5, so that's a base of 3. Height on the left is 5, plus the height on the right is 9. And then I'm going to add to that my next one. So I'm going to go 1/2. The base goes from 5 to 6, so that's a base of 1. Height on the left is 9, height on the right is 10, so 9 plus 10. And then lastly, I'm going to grab that next one. It goes from 6 to 8. Gives me a base of 2, so I'm going to go plus 1/2. The base is 2. Now I need the height on the left, which is 10, plus the height on the right, which is 11. Okay, so now when I go to calculate this, again, I'm trying to make my math as simple as possible. You usually don't get calculators on these questions. Every now and then you do. I'll just divide out a GCF of 1/2. And I'll kind of just multiply my final answer by 1/2. So I really have 2 times 5, so I get an area of 10. Plus 9 and 5 is 14 times 3. That gets me 42. Plus that's 19 times 1. Plus 10 and 11 make 21 times 2, gives me a 42. And then I'll add those up and take half that answer. So I think that gives me 1/2 times 113. So I'll just call that 113 over 2. And again, approximately 113 over 2. So now the question is, does this approximation overestimate or underestimate the actual value? Give a reason for your answer. So all we know is that this function is concave down. Okay, so let's make a big note there that we know this function is concave down. So here's what I'm going to do. I'm going to draw myself two concave down functions. One that's increasing and one that is decreasing. So this is concave down and increasing, concave down and decreasing. And then I'm going to draw in a trapezoid in each one. I'm going to make one big trapezoid. So up on the left, up on the right, connect. I'm going to go up on the left, up on the right, connect. So notice it didn't matter if I increased or if I decreased. Because the function is concave down, the trapezoid is an under approximation. Okay, so the trapezoid is less than the actual value. And my reason is that r of t, or r double prime of t, is less than 0 because it's concave down. And don't say it, make sure you talk about the actual function. R double prime of t is concave down. Alright, so we're going to integrate from 1 to 5 of radical x squared minus 1 dx. And we're going to do a trapezoid with 4, and I missed the keyword, equal subintervals. Okay, so because they're equal, we're going to use our little trick. We're going to find the width. So we're just going to take the difference in the bounds, 5 minus 1, and divide it by the number of subintervals. So I'm going to get 4 over 4, so each one is going to have a width of 4. So again, I turn this into a tabular. It's easier for me to see. You're welcome to do as you choose, but I like the tabular method. So I know I have to go from 1 to 5, and they're going to have equal intervals. So the first one's going to go 1, 2, 3, 4, 5. Easy enough. Again, just double check. You have equal intervals, 1, 1, 1, 1. And you have a total of 4 of them. Now you need to get the heights. Heights are simple. If you know x, you know y. So I'm going to plug 1 in. 1 squared is 1. 1 minus 1 is 0. The square root of 0 is 0. 2 squared is 4 minus 1 is 3. So it's a little ugly. That's radical 3. 3 squared is 9 minus 1 is 8. So I'm going to call that radical 8. 4 squared is 16 minus 1. 5 squared is 25 minus 1. So I get radical 24. So again, they may not be the prettiest, but that is okay. So now we're going to do our trapezoidal Riemann sum. So I'm going to go 1/2. Again, I write it out for myself. Base, height 1 plus height 2. So I have it in front of me. So 1/2, my first base is 1. Now, in fact, aren't all the bases 1 since it's equal? So hopefully you would agree that every trapezoid is going to have the same 1/2 in 1. So I'm actually going to pull that out as a GCF, and I'm just going to go through and get my heights. So the height of my first trapezoid is going to be 0 plus radical 3. Okay, so let me again tell you what I did. Every trapezoid area I do is going to have a 1/2. Every area is going to have a base of 1. So I just pulled them out as the GCF. So I'm just going to get this height plus this height. 0 plus radical 3. Now I'm going to go to the next trapezoid and add their two heights. So that's radical 3 plus radical 8. And then I'm going to add the next two heights. That's radical 8 plus radical 15. And I'm going to add the last two heights, radical 15 plus radical 24. Okay, so I just pulled out that is the GCF. If you want to write each one out individually, that is perfectly fine. And then I'm just going to add what I can. So 1/2 times 1 is 1/2 times, that's going to get me 2 radical 3 plus 2 radical 8 plus 2 radical 15 plus radical 24. If I can simplify anything, I will. So that's 2 radical 3, again 1/2 in front. This becomes radical 4 times radical 2, so that becomes 2 radical 2, so that's going to be plus 4 radical 2. 5 and 3 don't break down to anything. I could do a 6 and a 4, so that's going to become a 2 radical 6. So basically, excuse me, none of those can go together, so I'm literally just going to say it's 1/2 times this junk, and that's my approximation for that area. All right, so again, a similar problem from yesterday, same table in fact, but we're going to change the question here. And this is such a big deal on our AP, is being able to correctly justify what your integral is saying. So it says, using correct units, explain the meaning of the integral from 0 to 12 of p of t and 1/12 the integral from 0 to 12 of p of t in terms of the water in the swimming pool. So let me just remind you, water is pumped into a swimming pool at this rate. I want you to, if you're only going to write one thing down, P of T is cubic feet per hour. And then obviously the table here. So we know what P of T is measured in, and we have this table of values. So let me just remind you of something, and you probably need to put this in your notes here. Let's say position is in meters, and you take its derivative. If you derive position, you get velocity. Therefore, it now becomes meters per second, we'll say. When you go to get acceleration, you're going to get another rate, so meters per second, which of course is just meters per second squared. If you were to take another derivative, which you physics people I believe is called jerk, you would get meters per second, or meters per second cubed. And you could go on all day here. I don't know what they're called, but you could go on all day. Every time you take a derivative, you are adding on a rate. Now, since an integral is called the antiderivative, every time you integrate, you are taking off a rate. So when you derive, you add on another rate, right? You're going to add on a rate. When you integrate, you're going to go backwards. You're actually going to take off a rate. You are the antiderivative. You are going against the derivative. So if you had meters per second squared and you integrated, you would go backwards to get meters per second. If you integrate meters per second, you'd go backwards to get meters. So let's take a look at these units. P of T, they tell you right here, is feet cubed per hour. Feet cubed per hour. So if I integrate feet cubed per hour, I'm going to lose one of my rates. So I'm going to lose the per part, I'm going to lose the per hour, and I'm just going to get feet cubed. Okay, so how are we going to write this integral up? So we're going to say the integral from 0 to 12, and this needs to be in your notebook perfect, so you can reference it, is the change in Okay, so let's talk about what the change is in. If you had cubic feet per hour and you ended up with cubic feet, what's measured in cubic feet? Well, of course, volume is. It's the change in volume of the water and now here's the important part. You have to, well, it's all important, but you have to establish what the units are going to be. In feet cube or cubic feet. Okay, so we have to establish what our new units are going to be, and we have to talk about the bounds. From t equals 0, and they were hours, 0 hours, to t equals 12 hours. Okay, so the two key things I want you to highlight are you have to talk about the units and you have to talk about the bounds. Okay, now what's the difference between that and me throwing a 1/12 in front of the integral? We just talked about this the other day. You have 1 over that b minus a in front. You now have the average of something. Okay, so we're not going to say average value. We're going to put it in terms of the context of the problem. So what are we averaging? Well, we're averaging P of T. So let's go back and look at what P of T is. It is the, and again it's right in here, it says it every time, you just have to read, it's the rate of cubic feet per hour that water is being pumped into the swimming pool. That is what P of T is. It's the rate in cubic feet per hour that water is being pumped into the swimming pool. So as I go to write this, I'm going to say 1 over 12, the integral from 0 to 12 of P of T dt is the keyword being average. Let's highlight that. It's the average what? Well, it's the average of P of T, which we just said That's the rate at which water is being pumped into the swimming pool. Okay, so we have to talk about our bounds. That's the next key thing. So if I integrate P of t, which was feet cubed per hour, we're going to lose the hour and we're going to get feet cubed. But we are now multiplying by 1 over 12, which is hours. So you're actually getting the same thing. Feet cubed per hour from t equals 0 to t equals 12 hours. So one of the big things that messes people up is the units on this average. So again, I took that P of t, which was feet cubed per hour, I lost the hour, so I got feet cubed, but now I'm multiplying by 1 over 12 hours, so it basically comes back on. So we're going to get a lot of practice tomorrow with all the Riemann sums. We'll focus mostly on trapezoid, but we'll tackle all of them again tomorrow. So have a great night, and we'll see you then.